Oh, hello there. Don't mind me dropping everything. Oh god, I gotta recycle. Hey guys, what's going on? Memes here, yes. We seem to be, well, technically late, but on average, earlier than what we normally do. And what we're going to be looking at today. All right. Now, as a professional YouTuber, I can hear myself in my ear. That is good because that means it's actually broadcasting the way it was intended. All right. Good. So, what are we going to be looking at today? So, we're going to be looking at something a wee bit different. Um, this was just something that I randomly came across and I started to fall asleep to last night, and it got the old noggin a jog. Well, I am not a quantum mechanic nor a cosmologist. You could talk to, I don't know, baby, Professor Wolfram, Professor Keating. You talk to those folks. They are actual academic type folks. But I came across a short, I believe the gentleman referred to it as a briefing about things he could share as a retired Department of Defense researcher. Um, it reminded me of something that I learned about many years ago when I took a motorcycle training course. So it's very interesting. But welcome, Apollonie. Good to see you. Good to see you. Hopefully all is well. Hopefully you're not getting caught up in any weather. Thank you. Thank you for making sure we get the stuff and things that we need. But let's not belabor the point. Let's get right into it. Let's share with the class here. No, I need to push the right buttons. I swear I know how to do this stuff. Okay. So the following here is oh, I make it better. Okay, maybe. Okay. Make it a little darker. Give it theater mode. Okay, so this is from the alternative propulsion group. It's a lot of times we'll talk about different alternative propulsion styles and kind of goes into some of the UAP community and stuff. I don't really spend that much time there just because my general MO is to not lessen the readiness of the United States Armed Forces. But some of the things that I heard here seemed they were very intriguing, and it got me to thinking, are we missing something? Are we missing something that's just right in front of our noses? So let's get into this. So this is from Jamie Childress. As we can see from the description here, is an aerospace engineer. He is now a Boeing Technical Fellow, retired, former Department of Defense research engineer. And he starts talking about some of the apparent characteristics of space-time, or what is believed by the general theory of relativity to be where we live. So let's make sure we got the volume and stuff. As you see, the beginning of this is space-time is a material, whatever that may or may not be. So let's get into it.
So, when Tim and I talked about having me on his show, one thing that, I had to try and figure out, which was what kind of stuff could I realistically talk about? And that's because I, spent, 40 something years working for the Department of Defense and for Boeing as a researcher. So I'm a now retired Boeing Technical Fellow. And during that time, I spent most of my career developing advanced one-of-a-kind systems or vehicles, invariably involving research into advanced physics. And so as a consequence, I have to sort of worry about whether something that I say or reveal is either proprietary or classified or whatnot. So in coming up with this topic, it had to be pretty generic. So let's just march on and go on to get launched here. So
okay, so he seems to be being honest. It's like he worked for the Department of Defense. clearly there are things that he cannot publicly talk about. I totally understand that. I respect that, because you don't want to go around sharing state secrets. That usually doesn't go well. But it's very interesting in the way he kind of presents this material, because he's straight up. He was asked to maybe talk about this, and there are some things that he can talk about and some things he probably cannot talk about. Totally respect that. But within the things that he is talking about, that he is putting out there publicly, it really got my noggin a jogging. Um, Collie, now I know we had some discussions when I was up there in Toronto. Now, I'm not saying any of that is the case, whatnot. Again, we look at what we have evidence for. Because, like, my dad, God rest his soul, he was an attorney. He always told me, means the truth is the ultimate defense, and you follow the evidence. And where the evidence might lead us, maybe it goes down one path, but one of the big things he talks about here is very often within science, we investigate belief, or what we believe to be the case, as well as interpretations. And that might make a difference. Oh, welcome, Rick. It's good to see you. Well, it's Rick, I think you're going to enjoy this, because Rick is commenting. I think everyone is asking the wrong question. What is the ether? Question. Is it material? Well, this is a very interesting thing. Golly is commenting that she believes space is a compressible, thixotropic, dielectric superfluid. Flows in a dielectric fluid, causes charge separation. Charge is an artifact of flows in mass central space. Well, Rick, let's continue, because it's posed that way, and I think a lot of folks consider that perspective, of that we have an idea in our head, but one of the things he's touching on is ideas lead us in certain directions. So I won't belabor the point. Well, Rick is commenting that he thinks in terms of what space-time, what must space-time do, aka we believe there's stuff, and then things happen. I'm gonna play this just because I think you guys are gonna like it.
So this briefing really is not so much a technical briefing about the details of various space-time effects so much as just a way to think about space-time, and how changing the way you think about space-time maybe changes the things that you think you can do with it. Right. And so given the APEC audience, I'm going to assume that everybody is very familiar with a lot of the aspects of space-time that maybe the average person is not. So bear with me if I mention things that you're very familiar with. So, I mean, we'll just start off with space-time. Just what is space-time? So space-time is the stuff between everything else. It's the stuff between the stars. It's the stuff between subatomic particles. And because subatomic particles are small, but atoms are very large compared to the size of the subatomic particles, you are almost entirely space-time. So every object around you and you yourself is almost 99.99999 something percent space-time. So,
okay. Full disclosure, I'm sympathetic to the phrasing here. You can see, space-time is the stuff between everything else. I agree. It's you could say it's a simplistic phrasing, but I think see that's the interesting thing, Rick. I don't at least from what I recall from when I was listening to this, and again, I was falling asleep to this, and I'm just like, huh. He doesn't really talk about actual propulsion. It's kind of framed that way. It's like the science of interstellar travel. I don't really think I don't remember him talking about that. Again, I could be wrong. I was falling asleep. Kali is commenting, space-time obeys gravity. That's all we need. Well, I would say that's probably a winning perspective. Uh, uh, that is interesting. That is interesting. He wants us to do stuff. Well, I think many of the folks in one of the things with the alternative propulsion is that they're looking to, I don't know, you do. Wait, was it? They'll talk about different things like the Alcubierre drive, like a warp drive or something like this, or all these theorized advanced things. But as you follow up here, the trouble is we don't yet know what it is. So, but particles are made of space. Well, that would well, at that point we would kind of be insinuating that space-time is like fundamental. And some people go back and forth about that. So within the general consensus, to my knowledge, we don't really know. Welcome, Poindexter. We're about to get into a little bit of speculation, and I'm gonna add I am adding commentary right now. But the amazing thing, and again, I'm not a quantum mechanic. I'm not a cosmologist. I almost said cosmetologist. But I am none of those things, but I occasionally will notice patterns and things will strike me and start ringing bells about things that I remember in a different form. So let's continue with that right now. So let's get into it. So he's claimed, this is Jamie Childress, and he is a former Department of Defense researcher and now currently a retired Boeing Technical Fellow. So Boeing is one of the largest aerospace companies in the world. So you can take that for whatever you think it may or may not be. Let's continue.
So in fact, pretty much everything ultimately is space-time. And so, but because this is a discussion about really how to think about space-time, not so much exactly what space-time is. Before we talk about, the science of space-time, let's take a little detour into science. And this is something that I'm very, very well aware of because, for 40 plus years, I was, a research engineer, which is effectively a scientist. And so one thing I learned in that time is that science is not essentially a pile of data or a pile of results, if you will, but science is really how you think about the data, or you think about a test, or you think about what it might be going on. And and invariably, a lot of my own career was spent researching things where nobody knew the answer, right? There wasn't a cookbook answer, nobody knew. So two people could look at a pile of data and oftentimes come up with very, very different conclusions. In some cases, completely diametrically opposite conclusions.
Wait. Hold on. Is he saying that people might have different opinions on what's going on based upon what they see in front of them? Oh, whatever. Imagine that. That's a very good point, Kali. Apparently, and again, it's price of participation may vary. One thing to remember is that maybe none of the most famous scientists actually agree on what space-time is. You have a whole lot of different perspectives. It's Professor Einstein was fond of a steady state, but then again, adding the cosmological constant for his own preferred view of the world was apparently one of his biggest blunders. And then fast forward, I don't know, 50, 60, 70, actually, no. It was 1915. Okay, so 99 would be like 84 years. It was like back in 99, where apparently it looked like, oh, there appears to be a cosmological constant. Oh, things seem to be accelerating. Now it's like, oh, is it stronger before? What is going on? we seem to have this data. We look at the CMB measurements via Planck, and we get a particular number. We start going off farther into the cosmos, and things seem to get weird. Hey, maybe things were faster. Maybe things were more energetic. Maybe it was a much hotter, denser state. That seems to be what we believe with our standard lambda CDM, lambda cosmological constant, and then a cold, dark matter as the primary mass within our universe, with a little sprinkling of like 5% of the stuff we can actually see. So that is okay. So if Einstein and Schrodinger had different opinions, oh, imagine that. Humans with opinions. Is this why we can't have nice things, or will this lead to nice things? I cannot say, but let us continue the discussion on science and perspectives.
Right. So, so kind of to illustrate that, we're going to perform a simple test, and I myself am an experiment guy and a test guy, not a theory guy. So as a consequence, we're going to run a little test, a little experiment. And so that experiment is on the next chart. You are going to see a grid of geometric shapes. And what I want you to do is count the number of hearts among those shapes. And I'm going to give you 7 seconds to do that.
Right.
Okay, so everybody's ready. And here we go. You got 7 seconds.
3, 4, 5 hearts.
Okay. Time is up. So hopefully, most of you discovered that there were 5 hearts on the previous page.
I can count. I can count to 5.
So, the real test here was not to discover how quickly you could count to 5 by looking at the chart and finding that there was 5 hearts there. The real test here was for you to discover what you didn't see. And so I told you to look for hearts. And so, presumably you did that.
Yeah, I saw hearts.
But ask yourself the question, how many white pentagons were there? Because there was lots of different shapes. And how many black pentagons were there?
Wait. Hold on. No. You asked us to search for hearts. I searched for hearts. I counted the 5 hearts. What more do you ask of me? That's the solution. It's why. Wait a second. Is he saying we should pay attention to the things that maybe we're not looking for? Imagine my shock. Continue, good sir.
And so, to help you sort of do that, let's conduct a little quick visualization thing. So kind of close your eyes for just a second. I'll close my eyes too, and we'll think, okay,
close my eyes.
Let's take a second and go, well, how many white pentagons were there? Imagine it in your mind.
A number?
Okay.
I don't know.
Hopefully you have a number in your mind of how many white pentagons there are. Unless that number is 0, you imagined those white pentagons.
Oh.
Because there were no white pentagons.
Oh.
There were some black pentagons, and actually, I myself am not certain how many black pentagons there were, but there was a handful of them.
Oh. Wait a second. Are you saying that inferring that there were white pentagons, but there were no white pentagons, I might be mistaken? Because I was going to say between 4 and 6, because that seemed like a good guess. But then again, I wasn't looking for them.
This experiment really shows is that more than likely, when I told you to look for white pentagons, even though they didn't exist, you imagined that they did exist. And you may have some vague notions to how many black pentagons there were or how many stars there were, because there was other shapes in there. But you don't really have a very clear idea. You certainly have much less clear idea than you had for the hearts. And what this illustrates is that you find what you're looking for, and you tend to ignore the rest. And we like to imagine that science is not this way, that science is really, boom, yeah, we've got this, man. But, having been a research scientist for 40-something years, I'm here to tell you that that's not true. That you can look at a data set, and if you're not looking for something in particular, it's likely that you don't see it.
Wait. Hold on. Okay. So, not to belabor the title of this, but as you can see, there's some certain words right here that I still have typed in. Basketball Gorilla Original. What in the Sam Hill am I talking about? Okay. What in the Sam Hill am I talking about is this right here. This was something that was shown to me, or one of the versions of this, back in probably the early 2000s when I was taking the motorcycle training class. Okay. This is the selective attention test. Let's play this beautiful bean footage. All right. Full stunning 480p.
This is a test of selective attention. Count how many times the players wearing white pass the basketball.
Ready? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
How many passes did you count?
Got 15.
The correct answer is 15 passes.
Yay! I can count to 15.
But did you see the gorilla?
Wait, what? The gorilla? Wait a second. Wait, hold on. Wait, hold on. The gorilla for like 5 seconds walked
This
across
video
the
is from
stream.
research by Daniel Simon.
Wait. It walked across this. Oh. Hold on. The gorilla? Okay, the gorilla's there for what? The gorilla's there for like 7 seconds. Okay. He comes onto the middle. He literally beats his chest, and then he keeps walking. Okay. Why the heck am I showing this at all? Okay. So I remember the first time I saw that. I was taking the motorcycle training class, and they play that because you go through, you count, and then it's like, who saw the gorilla? It's like, gorilla? What are you talking about? You go back, as soon as someone mentions the gorilla, you're like, of course there's a gorilla. But if you were just paying attention, you're focusing on passing, and I've counted the precise number of times the people wearing the white shirts were passing the ball around. We got 15. Yeah, I got the correct number. Now at least for me, not everybody. Some folks totally see it. That's fine. At least the first time for me, I totally missed the gorilla. You had to tell me it was a gorilla, and then I noticed it was a gorilla. The reason why I'm showing that is just because this particular presentation, some may say a briefing, not releasing anything that he might be under a potential NDA for, is highlighting that we very often find the things that we're looking for, but if we aren't looking for something, there may be something as significant as a potential gorilla that we might have missed. So that's the whole reason for showing this, because as soon as I heard that, I'm just listening last night, I'm like, okay, this reminds me like that portion in the motorcycle training class. Why do they show that? Because a lot of times, if you're driving a car or a car in New England, you may sometimes grab your car keys, throw in your car keys, and then go drive your car down to Harvard Yard, but you can't park your car because there's no parking in Harvard Yard. But basically, if you're driving a car and you don't see a lot of motorcycles and you don't drive a motorcycle, you might not be looking for a motorcycle. That's one of the reasons why a lot of motorcycles have louder exhaust, so you may pay attention to what is going on there. And then some folks just also like to be annoying. There's a very broad distribution across humanity, I claim. I think it's fascinating, though, that we have a gentleman who happens to be a retired aerospace engineer, having to work for the Department of Defense, and he's highlighting the same thing that they do in the motorcycle training course when he's talking about science and things that we might be looking at. So that's, you can take that as you will. Let's see. What discoveries we found JWST to find the most interesting? I'm probably gonna go with Kali. Little red dots. Little red dot. Hey, Rick is agreeing on the little red dots. I would have to say the little red dots because it's like, we still don't know. It's like, oh well, that maybe a supermassive black hole, maybe it's a larger galaxy. Now, Fraser Kane had an interview, I think like 3 or 4 days ago, with a gentleman who at one point was like, okay, well maybe it's like a million plus solar mass like star or something. And at one point during the thing is Fraser is like, do you have any other crazy ideas? And to the gentleman's credit, he's from like the University of Austin. He's like, you want something crazier than a million plus mass solar mass star? And Fraser's like, well, yeah, you already said it. You've normalized it now. Now I need something crazier. So the researcher's like, listen, this is a crazy thing I'm suggesting, but based upon what appears to be going on, it appears to be around the temperature of the sun, but so much more luminous. What is going on here? He is hypothesizing. Okay, he's making a guess based upon the data. Now, perhaps it could be something else. Perhaps there's a missing gorilla we haven't accounted for. I don't know. All right, the deep, deep fields of what's going on. It's okay. See, it's number one, I slightly conditioned the audience. And again, some folks, first time with no prompting, you might see the gorilla. And some folks do. That's first time I did not. If you're prompted, oh yeah, there's a gorilla in there. You're like, okay, yeah, blah, blah, blah. Oh, look, a guy in a gorilla suit tweets his chest and then just walks off the screen. It just boggled my mind just because it reminded me so much of that. All right. Oh no, Mike, the gorilla! Be wary. They might be coming for you. I'm just playing. All right, let's continue. We still got like 25 minutes to get through.
And so, looking for material properties in space-time really helps you find them. So, and that's a critical thing to know. And so, which leads us into yet another thing, really, which a lot of people that sort of are on the outside of science don't really realize, is that belief is critical in science. So whether you believe in something, you don't believe in something, that really determines a lot of what you do or think about in a science experiment. So, if you believe that space-time is nothing, then it's really pointless to try and do research into how to touch it, right? However, if you believe that touching space-time is possible, that pretty much changes everything. And one of the things that it changes is that if you believe in something, you'll spend research dollars chasing it. And right now, there's really almost no significant funding for the idea of touching space-time.
Okay. So to kind of sum up what he just said, belief is critical in science funding. If you think something might be able to be done, or we got the potential for doing something, well, yeah, no, you can invest money in that. If you do not believe it is a thing or possible, why the heck would you spend money on something that's impossible? Now, there may be the caveat here of Arthur C. Clarke's quote, "The only way to discover the limits of what's possible is to venture a little further into the impossible." Now, this may come down to the perhaps difference of opinions and beliefs about what may or may not be going on here. So let's continue.
I mean, we spend all kinds of money on all kinds of things, but we spend almost no money. Certainly, no major government funding, certainly, in figuring out how to touch space-time. And treating space-time as a material, that suddenly makes quantum space research mainstream. So, in the APEC and Tim's audience in general, very interested in quantum space propulsion research, right? But thinking of it as a material suddenly changes how possible that is. And a number of years ago, I gave essentially an internal TED Talk at Boeing to a bunch of Boeing vice presidents and whatnot. And that TED Talk started off with me saying that developing something is rarely about what is possible. It is almost always about what people believe. And so
but belief seems to couch many of the things that human beings do. So, that seems like a pretty accurate statement there. Okay, so Rick is postulating what could be going on there that may explain these effects. I have no comment at this time, as well as the slightly jabby comment of mainstream, quote unquote, is defined as funded, quote unquote. That tends to. It's hard to argue with that point, but let's continue.
That is very, very true. So, you don't spend time and effort to try and develop something unless you believe it. That's the bottom line. So this talk is really about, let's see if we can help people believe that space-time is a material, and then that may change their thinking. So, one of the reasons that space-time has been treated as nothing for a long time is that back in the 19th century, space was called the ether. And it was believed that these ether vacuum particles transmitted light, or photons. The concept of photons didn't really exist too much back then, but it transmitted light, essentially the same way that sound is transmitted particle to particle. So vacuum ether particles transmitted light just the same way air particles transmit sound. And then back in 1887, the famous Michelson-Morley interferometer test showed that this wasn't true. And so in that test, they had two perpendicular mirrored arrays that formed an interferometer, and the picture in the right here is an interferometer pattern. And if that pattern is circular, then that shows that the speed of light in both directions is the same. And the theory behind this test was that the ether wind, if these particles existed, then Earth's own rotational movement as well as movement around the sun would be detected in this interference pattern and would show a bias. But it didn't.
So basically, all right, we take a measurement at one point, and then depending on our directionality and where we are to the sun and everything, at some point you would expect, if there was the luminiferous ether as had initially been postulated in that form, we should be able to detect a quote-unquote ether wind. And there would be some difference there. However, we didn't really have a detection. And some people will say, okay, maybe it was a null result. We weren't quite sure. But what is generally believed is, as you said, is it was not detected. Okay.
Show a bias. It showed that it was the same in all directions. And so what that test did clearly show, and in fact, I remember when I was in physics class about 1 billion years ago in the late 1970s, that I did the Michelson-Morley interferometer test, and sure enough, there were no ether particles, and which convinced me that space-time was in fact nothingness. But what does the Michelson-Morley experiment really prove? And what it does prove is that these ether particles don't exist. There aren't particles that transmit photons, one to the other. And what it also shows is that space-time, even if we do think of it as a material, doesn't interact with photons. And that makes the speed of light constant in space-time. And why?
Okay. So for some reason, it's oh no, we seem to be supporting Einstein again. Why? It's like, well, something about this. It's something about electromagnetism, or at least the traveling of light as we know it, whether it's in quantized states of photons or it's just all different wavy intensities and stuff. It somehow knows how to do what it's supposed to do. That seems a little weird, doesn't it? Or maybe it's like Goldilocks and it's just right. Let's continue.
It makes the speed of light constant in space-time is because if photons are not interacting with space-time, then of course their speed of light would be constant in space-time because there's no interaction. And so, and speed of light is key to being constant is key to relativity. And so there's all these bits of data that say, well, yeah, space-time isn't anything, right? Ether is real. Speed of light shows that's quite true. And of course, Einstein is been proven to be true pretty much every direction that you look when you look at relativity. So so the physics treats the lack of the ether wind as proof that space-time is not a material. And that's not necessarily a crazy viewpoint, but it also doesn't jive with a lot of more recent facts. And so one of those which is interesting, how two things that look very much the same are treated very, very differently. So I'm going to assume that the people that dial into Tim are familiar with dark matter, but if you're not, dark matter is something that was discovered decades ago, which was shown to be effectively the thing that holds galaxies together. So our own spiral galaxy is held together to a large degree by dark matter and would actually fly apart if dark matter did not exist. Yet, dark matter, according to the very word dark, says that we can't see it, right? So the physics community assumes that dark matter is some sort of matter, which makes it material. So material and matter, it's really two different words that mean the same thing. And so there's lots of theories as to what exactly this dark matter is, but nobody's really claiming that dark matter isn't matter, at least not in the wider physics community.
Wait. Okay. Now, all due respect to Jay, we know that dark matter does exist. We got neutrinos. They are by definition weakly interacting massive particles, whatever the heck those may or may not be. Wavicles, this, that, flavor changers, I don't know. But however, within lambda CDM, it's often assumed it is cold dark matter. Now, neutrinos, for the most part, if it's going close to the speed of light, that's considered hot. So that would be hot dark matter. Now, very often within dark matter, you'll hear something like perhaps there's an axion or something like that. It could be something like this, or maybe it was the right-handed neutrino, although there does seem to be evidence now suggesting that, I believe it was Professor Turok's stipulation for his, was it minimal lambda CDM, whatever it was there, stating that the dark matter could be the right-handed neutrino. It would be very massive. There seems to be evidence now suggesting that that's either ruled out or evidence like probably not the case. And at that point, it's like, well, why does the universe seem to have a left-handed bias, quote unquote? Because if you're doing this standard view, it's like, we seem to have this interaction between left-handed neutrinos and then left-handed antineutrinos. What is going on there? It seems to be weird and currently outside the standard model. But the general point here is, well, wait a second. If you run into the assumption that space-time is not a thing. It's just emptiness. It's just empty space. But dark matter is a material. Maybe. Why do we say that? Well, that's what everyone else says. So, I mean, everybody couldn't just be wrong. I mean, occasionally everybody is wrong. Like, occasionally for like the caloric fluid and everything. And I have heard Stephen Wolf from Conjecture that he tends to be of the opinion that whatever dark matter may or may not be, it's going to end up being something along the lines of the caloric fluid of our time. That was one of the original fluids of heat. It's like, well, heat seems to flow, so maybe it's like a fluid. And then we realize it's like, well, heat is just basically the energetic release of vibrating particles, whatever that stuff may or may not be, molecules, atoms, this, that, or the other thing. So as we learn more, we're able to find better explanations to what the heck is going on there. In the Michelson-Morley experiment, I think it was ruling out it was either kinematic or non-kinematic ether, something like that. So the science of interstellar travel is the subtitle of his tide, asserting that the ether doesn't exist. I think that was the perspective of what is going on generally within science. Maybe he does. I don't know. I'm not familiar with his research. Well, dark matter isn't matter. I mean, Rick, the blasphemy. Yes, you might be a crackpot number 6 if you think that dark matter isn't matter. I mean, well, to be fair, I think Neil deGrasse Tyson actually said it well. I've been articulating and triangulating a series of what I believe to be fascinating clips of what is going on. And in one of them, Professor Tyson is saying something along the lines of, to be fair, dark matter, a better term for it is dark gravity. It appears to be gravity that we can't really see what is causing it. There's more gravity there than visible matter than what we can see. And that seems like a very strange thing. So that kind of goes into its well, okay. And also statistics are true. You can't fool all the people all the time. Let's just one real quick comment here. I'm trying to find the exact point. I need to find gravity. Let's see. So just real quick, I didn't find the exact point in it, but let's just go over to this tab real quick. Part of this discussion with this when this presenter was talking about how apparently the speed of light seems not to interact with space-time. Reminds me of something that Rick had mentioned in one of his presentations. It's we got the radical powers in here, which I would. It was interesting because he was formulating a different perspective on how to view these base units of reality by taking the square root of them. Thank you. And at one point, when you're going about in constructing the Planck unit of let me throw this in the chat for anybody that
okay, no.
Let me share just in case if anybody wants to check it out. You may find it interesting because it helped lead me to notice some interesting things, I would claim. But let's go to Wolfram Alpha real quick, because the interesting thing is, well, if we believe the speed of light is like a photon, well, how do we get photons? Well, you got to jiggle the electron so it can spontaneously emit a photon or something like that. So with our Planck units, one of the things that you can also end up taking away is from our base Planck units, you got big G, H bar, and C. Those are the primary three constants of nature we use to construct Planck units. But if we look at something like the Planck electric charge, so Planck charge, charge. Actually, let's do this. To Planck time first. Planck time, as we had see, got the square root of big G H bar, and the speed of light raised to the fifth. Okay. So the Planck length. The Planck length, we got that going on over there. All right, we got big G, H bar, divided by C, raised to the third, the square root. All right, same thing, different powers of C. We got a Planck mass. Square root of speed of light times the elementary unit of action, all divided by big G. All right. Don't worry. There's a point to this. There's a point. And let's go to Planck temperature. I'm actually not sure about this one. But okay. Oh, no, I guess, yeah. No, even with temperature, we still got big G. Now, the interesting thing is, remember, the 5 units you need to create the Planck units are big G, the speed of light, H bar, the elementary unit of action, the electric constant, and the Planck temperature. Now, you could swap out C with the magnetic constant, as Rick had pointed out last week, but ultimately, it still seems like you still need at least 5 to create these 5 Planck units. Now, the interesting thing is with the Planck charge, does anybody notice? Does anybody see the gorilla? Where's the gorilla? Is there a gorilla in there? I don't see no gorilla. Why? Because there ain't no big G, and you can't spell gorilla without G. I'm sorry. That was a horrible pun. But basically, we got, this ends up being the square root of 4 pi. And then this is C, epsilon naught, the aka the electric constant, because it says right there, and H bar, Planck's reduced constant, the elementary unit of action. This appears to be the only one of the elementary Planck units that doesn't seem to be a big G at all in here. Long story short is Rick had mentioned it in this video right here. So radical powers. That was something like you kind of see it. I just went through the Planck units, and then Rick had to kind of mention it. I'm like, that's interesting. And that's why when our gentleman over here had mentioned that, I'm like, got my old noggin a jogging. So yeah, let's continue.
And so it's assumed to be it's assumed that dark matter is a material, and we are currently spending, billions of dollars, running big science experiments, trying to figure out what this material is and trying to find it. And when you try and find something, you're actually trying to touch it, right? Because if you're, the way that you see something, if you will, is to measure it. And when you measure something, you have touched it. Either you touched it with photons or you touched it with some other way. You touched it somehow. In fact, all of the current investigations to try and find dark matter and figure out what dark matter is involve attempting to touch it in some way. And so it's very instructive to sort of look at, well, let's do a little comparison between dark matter and space-time. So dark matter, it doesn't interact with photons, and it communicates with ordinary matter via gravity. Well, that looks a whole lot like space-time. Space-time doesn't interact with photons. It communicates with ordinary matter via gravity, i.e. space-time warping. In Einstein's universe, space-time is the fabric of the universe. Yet, for whatever reason, the fabric of the universe is not treated as a material. It's treated as effectively nothingness. Yet, dark matter is treated as a material. So that kind of makes you like, well, that That just doesn't seem fair. Okay.
As a professional YouTuber, it's to quote Goofy, something's wrong here. That's the meme that comes to mind. And yes, counting is something I believe we can do.
So, one of the reasons that space-time continues to be treated as nothingness effectively is that quantum field theory allows for fields to be propagated in a medium and the mediums being nothing. So, for example, photons can propagate in nothingness via
electromagnetic field,
which is an electric field, which creates a magnetic field, which creates an electric field, which creates another magnetic field. And just keep adding that for forever. So, in that view, space-time can be nothingness. And so in the case of a lot of physicists, they think of space-time as being nothing. But one of the problems is that nothingness view really ignores the fact that those fields...
I'm not sure that many physicists believe it's nothing, because even generally it's like, well, the vacuum, quote unquote. Yes, the vacuum that seems to have a particular energy density, at least according to Planck and a bunch of other things. Again, maybe they're wrong. But apparently, and you'll hear it's like it's some virtual frothing foam of virtual particles and stuff. Wait. But I thought I was it. Wait. But what? It's a vacuum, but it's not a true vacuum. So as somebody that happens to be part Irish, so is it like no true Irishman? There's no true vacuum. What's going on here? Continue.
Those themselves, so let's say electromagnetic fields or Higgs fields or weak weak force or strong force fields, those fields themselves are part of the space-time material, and we can touch those fields, right? And as an example, so if you can touch something, it has to be real, right? So a couple of examples of the things that methods that we have used to touch the material of space-time is the Casimir effect, which I'll go into the Casimir effect a little bit later, but I'm going to assume that most people who watch Tim's show are familiar with the Casimir effect and virtual particles and string theory. So string theory is a theory of everything that includes as many as 11 dimensions, and which brings up essentially a major aspect of space-time, which is both string theory as well as the existence of virtual temporary particles and whatnot. That the most logical explanation for those is that there are other dimensions beyond our normal XYZ plus time 4D space-time. Mm-hmm. And so a material that's partially resonant in other dimensions is still a material, right? So no one says that a material inherently has to only exist in our 4D space-time.
So it's again, the whole concept of when people are like, oh, we can't test string theory. In theory, we can test string theory. We just, given current technology, we just need a collider about the size of the solar system to basically get up to around like 2 pi Planck energy or whatever. It's long story short was we need a probe. Basically, an elementary string is basically minimum of length times 2 pi. So Planck length times 2 pi is basically would be the length of a fundamental string within something like M theory, to my knowledge, or at least that's what I heard from Wolfram Alpha. So that's that, and even I think, oh god, there's a Cameron Baffa. He may have said that they're probing that maybe these extra dimensions maybe aren't that tiny. Maybe something's around a scale of around maybe the Planck mass. And so basically, I think they need to get down to around about 10 to the minus 8-ish meters to try to see, because some folks have said maybe gravity will change from 1 over r squared, or whatever the distance is between your two masses, to 1 over r cubed. Maybe that will explain things. And they're getting around to the magnitudes where they may actually be able to try to test something like that. But then again, measuring gravity is not an easy thing, even with all our fancy technology and everything. We've got what, maybe 5 significant digits, and we still got like decent error bars there because it's not an easy thing. It appears to be the weakest force, even though they technically line up. Gravity and electromagnetism kind of line up at the Planck force at your most extreme limits, and like at least that's how I like to think about it. But maybe there is something crazy going on. So let's continue.
So, depending on whether you view space-time as nothing or if you view it as a material, actually does change what you believe is possible, right? Because you can't reach out and touch or alter nothingness, but you can touch a material. And more importantly, for space propulsion and a lot of the things that the APEC crowd looks at, you can alter a material, right? So if you start thinking of space as a material and talking about space as a material, then suddenly that alters what you sort of inherently believe is a possibility.
Hey man, I went for Professor Carroll. I gotta wave my hands. I'm making some gravitational waves, yo. Now, is this something you're actually going to be able to detect? Probably not. I mean, maybe if you're standing right next to like a LIGO experiment, you're like bang on the table or something. Yeah, I would probably pick that up, but that's why you need to have multiple stations there to try to coordinate. And then you have, you would also hopefully have some optical data as well. So, and I believe there was recent, I think, University of Seattle. I think Rick and I think a few other folks may have pointed this out, where they actually had astronomical data of a supernova. They actually were able to coordinate, measure the gravitational waves, and at least within the theory and the error bars and stuff, gravitational waves travel at the speed of light. I don't know. It's kind of like neutrinos seem to travel at like the speed of light. And occasionally, hey, sometimes there was an Ethernet cord that wasn't quite plugged in all the way, and maybe the experiment may have had some greater error, but that does appear to be a thing that I guess seems to make sense in a way, or at least remembering it is easier. But let's continue about this briefing and what may or may not be going on in some of the characteristics of space-time.
So let's kind of review, if you will, the basic material nature.
There we go.
Of
That's the data set and gravitational waves.
Some basic material properties of space-time is that it's a material, but unlike any material made of atoms. It's not made of atoms, it's clearly made of something else. Exactly what it's made of, I think the jury's out on that. But one thing we do know with absolute certainty is that space-time does not interact with photons, and that because it doesn't interact with photons, speed of light is constant in space-time. And another thing we also know with certainty is that fields are residents of space-time, and not just electromagnetic fields, but all the potential fields, Higgs fields, everything. They're all residents of space-time endlessly.
That's where we live.
One of those fields is gravity, and some of the examples of gravity interaction with space-time is gravity waves. And one of the things we know about gravity waves is that they travel at the speed of light. And because we have gravity wave detectors like LIGO, and who have detected gravitational, major gravitational events in distant locations, the instant that you have a detector of some kind, so like LIGO, what the detector, the fact that it's capable of measuring gravity waves, what that tells you is that it's capable of reaching out and essentially touching space-time. So that gravity wave detector is actually capable of touching space-time because the act of measuring something, like measuring a gravity wave, is the act of touching it. And so LIGO effectively proves that gravity waves exist, and you can't have a wave in nothing, and LIGO proves that we can touch that thing because we can measure it. If you can measure it, you can touch it. And again, yet another fairly obvious thing is that according to Einstein, mass curves space-time, and we know that to be true due to things like gravity lensing in black holes, and you can't curve nothing. So space-time clearly can't be nothing, yet it's still treated by big physics as yes, essentially a something that is by and large nothing.
He was one of the phrases. He said big physics. I don't know. I don't think he's going to go on for a full rant, but he's saying some particular keywords that might resonate with particular audiences. So this is yeah, if you're talking about big physics, you might be a crackpot. Now, again, who knows? Maybe he's just out there. Maybe he's just completely off the farm. Let's continue. Even if this gentleman was a quote unquote crackpot, but I don't know. He seems to be a Boeing Technical Fellow, which is I think what happens when you're a high-end researcher and you retire on good terms. So he was giving what he had originally termed as a briefing of things that he was able to share in an abstract way without revealing anything that he should not. So let's continue. We can finish this off.
So let's go over again, like a little bit more about what space-time material interactions look like. And so space-time is a material that's filled with fields. And space-time is filled endlessly with these fields. And so probably anybody who's been, a frequent visitor of APEC is well aware of zero-point energy. In fact, looks like we're going to have a briefing on zero-point energy here very shortly. And what zero-point energy essentially says is, well, okay, the space-time, even if you take a chunk of space-time and wall it off from everything else, and you don't shine a flashlight into it, it's completely dark, it's completely, has no electromagnetic fields, that we're actively putting in there. We're not doing anything, it's just completely quiet space. That even so, that space is endlessly filled with all of the possible fields. So all of the possible frequencies of electromagnetic radiation and weak force and strong force and Higgs forces and gravity itself. And so all of that amounts to an enormous amount of energy. So every square inch of space-time is filled with an enormous amounts of energy. And so, some of the things that are inherently there are virtual particles. So virtual photons are essentially the temporary force mediator within quantum mechanics of effectively electromagnetism or other exchanges of fields, right? And another one that's they're always there, which is virtual particles or virtual electron-positron pairs, which are responsible for vacuum polarization. And so again, I'm going to assume that pretty much most people that watch this show are familiar with the Casimir effect, but if you're not, the Casimir effect is an effect which basically says, okay, the vacuum space is constantly filled with all kinds of fields that surround everything. But if I take two plates and I bring them closer and closer together, well, the fields that are surrounding those two plates, they come in all kinds of wavelengths. And if I bring these two plates close enough together, the closeness of those plates is such that it excludes some of the wavelengths between the plates, but all of the wavelengths on the outside are still there. And at some point, the force from all those wavelengths external to the plates actually brings those two plates together due to the radiation pressure from virtual photons pushing on the outside being greater than the radiation pressure from the photons on the inside. So that's the Casimir effect, and it's something that has been demonstrated, so we know that it's real. So the fact that we have the Casimir effect, we can measure that these virtual photons and that interaction is happening. Therefore, we have been able to touch space-time. So the Casimir effect proves beyond a shadow of a doubt that space-time is a material because we touched it via the Casimir.
Oh, the Casimir effect. I don't know. I don't know. Does that claim hold water? It's well, I don't know. There is no farm. Who knows? Off the farm, in the farm. Is it all just a farm? I don't know. Is this like the three body problem where it's like, all right, are we just turkey scientists just theorizing of what's going on, or are we some lower dimensional beings where some higher dimensional quote unquote shooter is just putting out a particular pattern that we're like, oh yes, that might make sense. It's that seemed to wear on some of the scientists, at least in the show there. Well, yeah, Rick, he might be bound by a lot more than tens of thousands of dollars. It's might be the whole treason thing. I don't know. What's going on? Oh, we're just within my realm of algorithms, a segment from I think one of the APAC, which is the Alternative Propulsion Conference, came up within my feed, and I was listening to it as I was going to bed, and I'm like, this reminded me of a couple of things. So if you go back to earlier there, we were going over. This gentleman does a test about human attention, and it reminded me about something that I had watched when taking a motorcycle training class back in the day. I won't completely spoil it, but it has something to do with the thumbnail. I did not just arbitrarily post King Kong there just because I like kaiju and wanted to use it as a thumbnail. I mean, that was a total contributing factor, but there is a point to it, I claim. So, wow. Well, these things happen. All right, so let's continue with what's going on. We're almost done.
Casimir effect. And the same is true for vacuum polarization. And vacuum polarization is where you have electron-positron pairs constantly popping into and out of existence from space-time, from some unknown zone of space-time. And those electron-positron pairs create a measurable effect called vacuum polarization on electrons, because they shield electrons from other electrons and from other various subatomic particles. And we know that they exist because they affect electrons. So they've got to exist if they are affecting electrons, that we can touch them literally through electrons. So another example of sort of space-time material interaction is dark energy. And again, I'm going to assume that the people on this call are aware of dark energy, but just in case you're not, dark energy is the thing that is causing the expansion of the universe to accelerate over time. And if you read the science material on dark energy creates negative pressure within space-time. Well, negative pressure is simply a word that means anti-gravity, only you don't have to say anti-gravity. So it's a practical matter. Dark energy is anti-gravity, but science hates the word anti-gravity, so they're sticking with negative pressure. Yet other, other evidence that of other dimensions in space-time is
well, actually, to be a lack of negative pressure. It seems kind of odd, but hey, this is our understanding. So, but oh yeah, I do dumb stuff every single day. Many would argue this right here was a very dumb thing to do, but I resemble that. So I don't comment on that at this time, Charlie. Let's continue.
Entanglement. So entanglement, defeats the speed of light, is faster than the speed of light, is effectively instantaneous. And for entanglement to exist, almost all theories of entanglement involve other dimensions besides our normal four. So entanglement, evidence of other dimensions. String theory, again, a theory of how the universe operates, and it has as many as 11 dimensions. So string theory is based upon the idea that there is a lot of dimensions, not just four. Virtual particles popping into and out of these other dimensions. And the universe is expanding in what? What is outside the universe? So, those are certainly aspects of space-time material. And
I've occasionally been told that's not a good question. It's what is outside? Wait a second. You just can't accept universe is expanding into what? That's a bad question. Really? Isn't that just the obvious question? Are you just saying that just because you don't have a good answer? I mean, that's the snarky thing to say. Maybe it is an ill-posed question. It's not like they're just going to say, just shut up and calculate. Don't ask questions. Why? It's not like you don't have answers. Because if you had answers, then you would be able to provide an answer. Unless that is the answer. I mean, we're not just giving people busy work. I mean, God, imagine that. That'd be rude.
One of the things that's worth discussing here is the fact that dark energy and dark matter were accidentally discovered. So no one was searching for them, and that's especially instructive in the case of dark matter. So dark matter, nobody was searching for it, yet they looked at the data and they said, well, man, spiral galaxies would definitely fly apart if it wasn't for something, and we're going to call that something dark matter, and it clearly is a material, at least according to our current best guess. There's this material, it's called dark matter. Well, as we just discussed, dark matter and space-time look a whole lot alike. And clearly, if you really looked at the data, you would conclude that space-time is a material, yet dark matter is inherently treated as a material. And so all that we really have to do to make space-time a material is have big science suddenly discover, well, hey, if we look at all the data, space-time is clearly a material, so let's call it a material. And the act of calling it a material sort of changes the game. And so one, a topic that often comes up here in APEC is quantum space-time propulsion in one form or another. And it's oftentimes, discussed as if it were reactionless. And my personal take is that it's not reactionless, that what might appear to be reactionless in our conventional 4D space-time is probably not reactionless when you include all of the potential dimensions in space-time. So, if you essentially say, well, okay, yeah, I may not be able to understand what this reaction looks like in my 4D space-time, that doesn't mean it's actually reactionless in some higher dimensional space-time, 5D space-time or whatever it might be. And that's true whether your quantum space propulsion is, some approach that allows you to swim through space-time via reaction to virtual particles, or whether it's a gravity-like effect. I mean, effectively, it isn't reactionless. It's actually reacting, against some dimension that we don't normally see.
Wait a second. You saying there's stuff that might exist if we can't see it? I mean, come on, if I can't see it throughout my polarized sunglasses, it must not exist, unless it was like a polarized UV thing, because then now it's filtering out that, but that's not the point there. Okay, fine. Maybe some folks, they're okay. How many dimensions do we need? Do we need 5, 6, 7, 8, 9, 10? As far as dimensions of measure, I would say about 5. But then again, that sounds a lot like Kaluza-Klein, and apparently there were issues with that. Unless we're missing the gorilla. Is there a hidden space-time gorilla that we are missing? I cannot say, but we got a nice Revolutionary War individual here talking about 1776. So, as a toxic male, I must click and at least finish this. So we'll get to a little discussion in about the next 3 minutes.
And so this brings us, ultimately around to where this talk, what this talk is ultimately about, and that is you've got to sort of ask yourself, well, why does it matter whether we call space-time a material or we just pretend to continue to call it nothingness? And the answer to that is that what you call something actually does matter. And like a prime example of this, since it's we've got the 250th anniversary of the American Revolution, is back in 1776, with the Continental Army, was called the rebels by the British and the patriots by the Americans. And the difference between whether you call them rebels or you call them patriots doesn't change the Continental Army one little tiny bit, right? The Continental Army is still exactly the same, regardless of what you call them. But funding flowed very differently. The British funded a whole bunch of people to defeat the Patriots, and the Americans funded, the Patriots themselves. So you're thinking in your funding flow according to what you believe. And so kind of keep that in mind, so that really ultimately it's all about funding. And so, I'm encouraging the point of this is to encourage people to think and talk about space-time as a material, both in, your discussions and in literature in your mind. And if you do that, it changes no physics theories and it changes no experimental data sets. But what it may do is change what you conclude from a data set, right? Because you'd be liking, okay, well, this is a material, and what does this data say about that material? And it also encourages you to believe that touching is possible, right? So, if you think something is a material, you inherently believe you can touch it. You may not know exactly how to touch it, but you believe it's possible. And so by treating space-time as a material in science discussions, it increases the research into direct interaction with space-time, right? Because if you believe something is a material, you are like, oh yeah, let's go touch that. And so that promotes things like gravity modification research. And it promotes things like research into quantum propulsion, whether that's gravitational or some other particle interaction that, of particles that inherently exist in spacetime. So treating spacetime as a material takes us to the stars, because we can't get to the stars with rockets. We can only get there through quantum, interaction with spacetime in one form or another. So that pretty much brings us to the close. So, go out and socialize the space-time as a material, and that actually can have an impact on research.
Cool. All right. Let's follow the good Boeing Fellows suggestion there. Go forth and socialize. Let's see where are we at. All right. Charlie's bringing up that apparently local geometry is not expanding. That was the whole. Is Brooklyn expanding? No, Brooklyn is not expanding. Then again, according to Echelon, Brooklyn is expanding at a highly accelerating rate. Something like that. Commenting, reality consumes dark matter and probably exhaust dark matter, around combustion, confused fuel and exhaust. Okay, I have technically kind of proposed a cosmological model, not necessarily based on that, but just based on maybe a similar premise. Oh no, the gorilla is a lie. No, my friend. Oh God, by the gods, it's a spherical gorilla. Yes. Assume a spherical gorilla. All right. Where are we? Okay, so yeah, maybe 21 dimensions. I don't know. I heard I was really like 26, which happens to be around the dimensional configuration of the Leech lattice or whatnot. Maybe you need 24, something like that, or you formulate it however you want. Hey, listen. Lego my Calabi-Yau. If you got the right Calabi-Yau, then I guess it's all good. You just let us know the initial conditions, your vacuum states. Bada boom, bada bing, we're good. Allegedly. Again, I'm not a string theorist. I would talk to Professor Whitten. All right. Yes, depending on Hey, one person's one person's terrorist is another person's freedom fighter. It's I would contest there's a certain level of morality that one could generally apply, mostly from Boondock Saints, but it's not what we're here for at this moment. Charlie is speculating that space-time is a composite. He's thinking about running it through some AI agent. Nerdy is grinning at our different stuff and things. Oh god, now we're going into banter between England and what they view as still the colonies, or so to speak, the states. Yes, there's a lot of friendly banter and stuff going back and forth. Of course, I just said the leech lattice. It's that has some interesting numerology you go through as your factor or let's go to the physics monastery. Let's just share real quick. Bada boom. Share screen real quick. Monastery. Where is it? The matrix determinants, blah, blah, blah. It's transform space. Here we go. Okay. So here's the thing. This is using similar to at least factorizing in this way. So the volume of a 24-dimensional hypersphere, this right here is 5 subfactorial, aka the number of permutations, and then this is 5 factorial. Long story short, this is 44, the magnitude of the exponent of the Planck time, and this would be the factorial, which comes out to be 120. And then this is 35, the exponential power for the Planck length. There's 18 for the Planck charge, 32 for the exponential of the Planck temperature, 8 for the Planck mass. And again, these are different exponents there. And again, this is some numerology, but it's numerology until it can explain more with less. Does it explain more with less? I don't know. But basically, if you divide all those by 4 pi with these exponential powers, you get that. And this also apparently happens to be the rho, or the density of the Leech lattice. So, okay, yeah, so it says all that stuff down here. So if you're interested in that, here's a link to that post from the Physics Monastery website. All right, including phase domain. Oh, nerdy. Oh, geez, now you're getting into the real nerdy stuff, aren't you? Oh, I see what you did there. Oh, let's go to our friend. The dimension of phase space. Now, don't ask me how I may or may not know this, but I know. Hold on, it's nothing. This is. So, if you want to talk about phase space as a volume, apparently, the Planck phase space volume is the elementary unit of action Planck's constant raised to the 3rd power. What precisely does that mean? I don't know. It's this is, and again, I ain't no Einstein or anything. I just have modern technology that literally says the thing. So if I am prompted by a nerdy rodent talking about what is it, phase dimensions, I'm like, oh, phase dimensions and stuff. I don't know about dimensions, but this is phase space volume, and apparently the dimensions are mass to the 3rd, length to the 6th power, divided by time raised, divided by time cubed. because it's a negative there, so it's in the denominator. All right, let's see. Ooh, absolutely not, Thomas. Definitely put that in the comments. Send that to me. I'm always interested in. This is why very often there was one discussion. I don't even know if I posted it, but at one point, my two postulates are math works and logs are useful. That's my general postulation. Math works, logs are useful. And then I'm just going to talk about things and present what I would claim to be evidence, and folks are free to disagree, and they have counter evidence or very good reasons why that's not the case. Listen, here's the thing. Do we want to actually figure out what's going on, or do we just want people saying nice words? Is the thing. If you just want people to watch and be like, yes, 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 boss, yes, absolutely, that's what we want to hear. This is something that even Kurt Mungle at one point admitted to. He's like, yes, there was at least one instance where I totally did something for the money and or just attention. He didn't disclose what it was, but just in my limited experience, the most attention I ever got on a live stream was on a satirical Breaking the Multiverse Thursday podcast with Fizz, when we just randomly brought up 3IA Atlas and we just satirically comment. Totally aliens. At that point, that was probably 3 times the highest number of people we've actually had watching a broadcast. What? Because we're talking about aliens, bro. People love that stuff. So I can just talk about that now. What the heck does that actually mean? That was for a satirical show called Breaking the Multiverse, talking about an interstellar object that apparently was leaving. You just use certain keywords. If you're in a culture war, you just add the term woke to something. It's so woke, or you can just call somebody a fascist or something, and you're going to get more attention. Why? It's standard salacious stuff. Does it help the issue? I think it's just hating on other folks or creating a salacious thing or telling people what they want to hear. It's like, tell people whatever they want to hear. Is it what they need to hear? Sometimes people just don't want to hear things. Some folks just want to hear nice things and things that they agree with. Welcome to the internet. But, oh God, Hilbert spaces. Jeez, this is, I believe, again, I'm not a mathematician. To my knowledge, it is I think according to Professor Baradas, our configuration space that could potentially be infinite according to the von Neumann axioms. All I know is in Planck dimensions. Hold on. Quantum speed limit. I think it's this guy. Where is it? This is Hilbert. Okay. It's one of these calculations. Projective Hilbert space, blah, blah, blah. Fabini metrics. Mangelson-Levison limit. That's okay. Maybe the Bremer limit. It's one of these things. Long story short is they have. Where's the radius one? It might be one of these other guys. Where is it? Because they talk about it after. I think it was this guy. The upper bounds. Might be under the Bekenstein bound. Okay, here it is. All right. So basically, if you do the dimension of Hilbert, okay, this is the dimension Hilbert space. It's the exponential of 2 pi. You got a radius, you got an energy, and you've got h bar c. Now, we'll go into it here. All right. Basically, long story short is if you plug in all those numbers, if you just put in the Planck length there, the Planck energy, blah, blah, blah. So let's just do it right now. So it's exp, well, from exp. So we're going to exponentiate. So we're literally multiplying it by e, the base of the natural logarithm. So we're going to do 2 pi Planck length, Planck energy. We're dividing it by h bar c. All right. Divided by h bar c. So basically the bending stiffness of space-time. You get this number here. What the heck is this number? 5. I didn't know what it is. What it is if you take off the exponential, what do you get? 6.283. Wait a second. That looks familiar. What is that, my friend? Oh, that appears to be 2 pi. So that means the Planck dimension of Hilbert space is literally e raised to the 2 pi according to this formulation. And since you can see, it's not a 5 there for the second digit, it's 4, 9. So like in elementary school, we round down. That's why Wolfram rounded down to dimension 535. So the Planckian dimension of Hilbert space is e raised to the 2 pi, but then again, there's some disagreement here because they literally say the following heuristic derivation for some constant k showing that k equals 2 pi revolves a more technical analysis. I just plugged in the limits of reality to as we know it, and it appears to be e raised to the 2 pi, which maybe that's telling us something. Maybe it's just maybe we're getting lost in the math. I don't know. Quasi impulse in the presence of quasi impute on the presence of innocent. Look at it. Okay. All right. Cool. Very good. Thank you. Well, I think a lot of people like to occasionally scream and throw things. Oh, who doesn't love aliens? Exactly. I liked Alf. Don't leave your cats out. Where are we? Okay. Hang on in my basement. I'm hanging out in my Hilbert space. It's e to the pi dimensions in Hilbert space and square footage. There we go. Maybe not. Maybe that's a good thing. Maybe that's an under representation. Every once in a while, Charlie, I consider it's not like people are fake. Listen, there are people that really know what's going on. Like you can have some deep discussion. The people that actually know things will occasionally say, I just don't know. Every once in a while, it's like I spent some time in corporate America, and it's like it's not like some folks are out there just literally just faking it the whole time to just get by and get yelled at by their boss as little as possible, as long as you can collect your bonus. I mean, I was one of those people, but then again, I'm a terrible, horrible, no good, very bad person. What do I know? You're welcome. Yes, nerdy is just hang out on the surface of a Klein bottle. Yes, as the rodent distorts and seems to invert but keep on going on. It's yes. Klein bottle is fascinating. It's what can we learn about these mysterious self-feeding bottles? I'm gonna stop talking there because I know where the discussion will likely go beyond that. Nerdy is claiming, I know less than not knowing what's going on. Well, that would make you the wisest among us, Nerdy. Ooh. I get one question. Make it good. Ooh. What's going on? Or can I change it to Sean Carroll's? Can I change it to Sean Carroll's question? What is the theory of everything? I want to know everything. I would say there was a lot of talk about dark matter. How about that? If we know it's red. Oh. Well, Nerdy's got it. What is your favorite color? Red? All right. Moon at Noon has answered, and well, that was from the Holy Grail. I was contemplating the airspeed velocity of an unladen swallow. Nerdy beat me to it. Well, guys, we just wasted our chance at figuring out the secret of reality. But you know what? I think red is a pretty good answer. That's selling itself just. I mean, here's the thing. It's, again, the statistical thing is, again, with the whole crackpots and everything, if you're going to do modeling, you'll see very often the standard distribution. Every once in a while, you'll see like the outlier out here, because you can never model the extraordinary. Now, you could view that as a negative statement and be like, oh, you can never model the extraordinary. It's extraordinary, and it's like, that's the weird stuff. One pronunciation is extraordinary. And if you statistically have a large enough count of quote-unquote people identified as crackpots, statistically, there's probably going to be at least a few folks out there that notice very interesting things. So that's my claim that there may exist some folks out there that are what I would deem as sufficiently crazy. Stephen Wolfram was highly skeptical when I shared that thought with him. But then again, his perspective is he gets lots of emails, like 600 emails a day. And a lot of times folks will start to go through it, and he was been very disappointed. So that's going to guide your perspective that you're like, it's not really worth it. That's why I did that whole like video on like, if you're going to send them something, send them a piece of ruleology, some orders of rules that are just the orders of rules. Because now you have something that, if that is the case, if the rules follow this particular structure, that is something that you have actually discovered. You had found a rule within reality as we know it, and those are the things of interest to him. So if somebody wants to send him something, he's like, please send me ruleology. So, and again, I'm paraphrasing there. Don't quote me, bro. How many opportunities get wasted? An uncomfortable amount. That's uncomfortable amount. Yeah. That was a good question. That was a really good question. Thank you. Okay, bottles and hops vibrations. All right. Thank you, everybody. All right. Ooh, do it. And the stuff you learn from nature, just even watching a spider weave a web is just fascinating. It's just read that as to get wasted. Okay, all right. We've been going for 130 or 1 hour and 37 minutes or so, and yes, we're gonna wrap it up. We're gonna be entering the 138th minute, so we've obviously gone 1 hour and 38 minutes. God, it's almost like our unit systems occasionally can confuse us. Maybe somebody should do a video that explains pellucidly what's going on. Maybe I should do one of those. So with that said, thank you for all who are joining and those who may be temporally joining us in the future for what may or may not be going on with reality itself. And stay saucy, my friends. It's open for a better tomorrow, and maybe together we can figure out just what is going on. So, peace out.